Now let us start with a simple problem, that is conversion of methyl chloride into ethyl chloride. Now it increase the carbon number. The reaction we have studied is Wood's reaction, that is reaction of haloalkanes with sodium in dry ether. So methyl chloride on reaction with sodium in dry ether. Two NaCl molecules are removed and we get CH3CH3. Now this is a symmetrical molecule in the sense if you place a mirror here, we get this group as the image of this one. So these two are similar groups. So on further chlorination of this ethane molecule with ultraviolet light and chlorine, we get ethyl chloride, where one hydrogen of any one of the methyl groups is replaced by chlorine. So that is conversion of methyl chloride into ethyl chloride Wood's reaction, and then free radical chlorination using ultraviolet light. Now coming to the reactions of haloalkanes, taking chlorobenzene as the example. Now chlorobenzene has chlorine with 3 lone pairs, and their chlorine can show plus some effect and minus I effect. And as I have seen earlier, chlorine provides a p orbital, especially sp3 hybrid orbital. This is having a larger size because the p orbital belongs to the third shell, and there the electron density is slightly less, so the mesomeric effect is not so effective, and again due to its electronegativity chlorine shows minus I effect, and hence we say the magnitude of I effect is greater than the plus sum effect of chlorine. Still it exerts the plus sum effect, so that lone pair of chlorine is given for bonding to maintain the valency of this carbon, this pi bond. Here we can take this as the pi bond, and this pi bond migrates in this direction, making the carbon 6 a negatively charged carbon and a p orbital containing a pair of electron. Now this pair of electron will convert into a bond pair with a simultaneous shift of this pair of electron, and then we get negative charge here and a lone pair. Now during this change, sp3 hybridization of chlorine changes to sp2. Now this thing will be repeated here also. The net effect is that the ortho and para positions in chlorobenzene are electron rich, we say. So electron density accumulates in ortho and para positions of chlorobenzene, but this electron density is not so much as the electron density in benzene molecule because of the minus effect winning over the plus sum effect. But the minus effect gradually dies away as it reaches the fourth carbon, that is the para position. So electrophilic substitution of chlorobenzene mainly gives the major product as the para substituted derivative, because inductive effect is minimum, or the partial positive charge at position 4 is minimum. And again during ortho substitution, chlorine is having an appreciable size, not so much large but a medium size. It is greater than chlorine, so there can be a steric interaction between the incoming electrophile and chlorine, so that in the transition state this slight steric effect may affect the transition state, raise its energy, so that ortho substitution is less observed. So the major product will be the para substituted product, mainly for two reasons: inductive effect dies away at para position, and then slight steric effect in the transition state for ortho substitution. Now, in chlorobenzene, we have seen that the ortho and para positions are electron dense or electron rich. Now, this molecule cannot undergo nucleophilic substitution mainly for the reason that the carbon to chlorine bond is having double bond character due to plus some effects. So, the breakage of this partial double bonded compound CCl bonds is difficult. So, easy nucleophilic substitution cannot occur in a chlorobenzene, but if drastic conditions are used, for example high temperature and high pressure, then we can break the CCl bonds. So due to partial double bond character of CCl bonds, easy nucleophilic substitution is not possible. And again, there are other reasons assigned. The carbon here, that is carbon connected to chlorine, so all other carbons are sp2 hybridized, means 1 out of 3 orbital is an s orbital. So the hybrid orbital has 1/3 s character, whereas for sp3 hybridization 1 out of 4 orbital is s orbital. So the s character of sp3 hybrid orbital is 1/4, whereas s character of sp2 hybridized orbital is 1/3. Since 1/3 is greater than 1/4, we say the carbon connected to chlorine has greater s character, and greater the s character, greater the electronegativity of that carbon, because s orbital is more close to the nucleus in any shell, and the attraction over the electron in an s orbital is maximum in any shell. So as the s character increases, electronegativity increases, and the bonding pair becomes more close to the electronegative atom, or the bond length decreases. Now another reason for now here the bond length for the carbon to chlorine bond in an alkyl halide or haloalkane is 177 pm picometer, or 1.77 angstrom units, and for a CCl bond in an aromatic compound, that is chlorobenzene, bond length is 1.69 angstrom units, or 169 picometer. So the bond length is less, and shorter the bond, stronger is the bond energy. So a short bond has a great large bond energy. Now another reason assigned is that when suppose chlorine is removed as Cl negative, then we get a phenyl cation. This cannot be stabilized by any electronic effect, so this is highly unstable, so this reaction cannot form at all. Now again, the pi electron density of the benzene nucleus. Pi electrons are not labile, they are always moving around the carbon atoms in a circular manner along the ring, and pi electrons are situated slightly away from the nuclei of carbon atoms. So this pi electron density of the ring will repel an entering nucleophile, where the nucleophile is trying to donate its lone pair of electron, and this lone pair of electron will be repelled by the pi electron density of the benzene ring. So these are the reasons assigned for for not occurring the nucleophilic substitution reaction. Now coming to the electrophilic substitution reactions of chlorobenzene. As I told earlier, the minus effect of chlorine is greater than its plus some effect, so the positions in chlorobenzene, the carbon atoms in chlorobenzene are less electron dense or less electron rich than the positions in benzene. We say the benzene ring in chlorobenzene is deactivated, in the sense its electron density is made lower. Now anyway, this will undergo electrophilic substitution reactions. Now halogenation, when carried out in presence of anhydrous ferric chloride, chlorine can enter in the ortho and para positions, because in the ortho and para positions there is electron density compared to the meta position. So chlorine enters the ortho and para positions, in the sense one H and one Cl remove HCl, and the Cl enters into the position of H. We get the ortho compound 1,2-dichlorobenzene. When H in the para position is replaced as HCl, chlorine enters the para position to get another dichlorobenzene, that is 1,4-dichlorobenzene. Para-dichlorobenzene is used as a moth repellent. Now nitration can be effected. We use a mixture of concentrated nitric acid and concentrated sulfuric acid approximately in equal amounts. Then in the medium, the electrophile, that is NO2 positive, that is nitronium ion, is formed. H2SO4 ionizes as H positive and HSO4 negative. Then nitric acid may be written as OHNO2. Then the lone pair of OH group, oxygen atom, combines with H positive, so it becomes OH2 positive. OH2 positive is a good leaving group, and again due to its positive charge, it completely takes up the electron pair in the bond, in this bond. So nitrogen loses its share of electron, and we get NO2 positive, that is nitronium ion, and that is the electrophile in nitration reaction. We get a replacement of hydrogen, as H positive is removed and NO2 positive enters into this region ortho. Here also H positive is removed and NO2 positive is entering in this region, and we get 1-chloro-2-nitrobenzene and 1-chloro-4-nitrobenzene. The para isomer is the major product, as I have told you earlier, maybe due to the very small partial positive charge in the para position exerted by the minus I effect of chlorine. And again, nitro group is a bulky group, so it can interact sterically with the chlorine when substitution occurs in the ortho position. So slight steric interaction may prevent the formation of the ortho product slightly, and so the major product is 1,4 derivative and the minor product is 1,2 derivative. Sulfonation is an electrophilic reaction where the electrophile is SO3H positive. SO3H positive is the electrophile. Again, H2SO4 can anionize to give H positive and HSO4 negative. Then HSO4 may be written as OH SO3H. Then lone pair of oxygen connected to H positive, so we get OH2 positive. Then due to its positive charge, oxygen is highly electronegative. The complete bonding pair of electron is taken up by oxygen, neutralizes the charge over oxygen. We get water and SO3H positive. Now this H positive is removed and we get a negative charge here that combines with SO3H, or here H positive is removed, here we get a negative charge and SO3H positive is getting connected, and the sulfonic acid group is given preference over the chlorine group. So in a UPSC system, higher preference is given to SO3H group. So when we start numbering from here 1, 2, 3, 4, so it is 4-chlorobenzene sulfonic acid, and then we get the ortho isomer, that is 2-chlorobenzene sulfonic acid. There again the 4-chloro derivative is major product. Now another electrophilic substitution reaction is Friedel-Gas reaction. Now it involves the alkylation and acylation of the benzene nucleus. Since chlorine is, we say, ortho-para directing, means the incoming electrophile is directed towards the ortho or para position. We get the ortho and para substituted derivatives. Now CS3Cl or CS3COCl in presence of anhydrous aluminum chloride, we get alkylation or acylation. If it is CS3Cl, we get alkylation. If it is CS3COCl, we get acylation. Now in alkylation, the electrophile is CS3 positive. Now CS3Cl combines with AlCl3. You know, AlCl3 is a Lewis acid because it can accept a pair of electrons since it contain a vacant orbital over aluminum. So into the vacant orbital of aluminum, chloride ion is entering. We get AlCl4 negative and CS3 positive. And this CS3 positive attacks the benzene nucleus. At the ortho position, H positive is removed and a negative charge created combines with the CS3 positive to get the ortho derivative. Similarly, H positive is removed from the para position. CS3 enters there. We get 1-chloro-4-methyl benzene, and this one is 1-chloro-2-methyl benzene, or we call it orthochlorotoluene or parachlorotoluene. Now acylation, there the electrophile is CS3CO positive or acyl cation. So acyl cation is the electrophile as usual. Hydrogen from the ortho and para positions are removed as H positive, and CH3CO positive enters into ortho and para positions. Now the major product will be the para substituted derivative. Now we give a preference to COCH3 group over Cl, and in the absence of Cl, the compound is called acetophenone. It's a ketone, acetophenone. Now here this is 2-chloroacetophenone, or we call it orthochloroacetophenone. Then this is parachloroacetophenone or 4-chloroacetophenone. Now the mechanism of electrophilic substitution reaction, it may be understood by this sequence. Now this pi bond will be shifting in between this electrophile and this carbon. So this pi bond will be rotating like this. When it reaches E positive, it forms a bond with the E positive. Since the two electrons are moving in this direction, one electron is given to E positive so that its charge is getting utilized, and since this carbon loses its share of electron, it gains a positive charge. Now the thing is that chlorine can stabilize this carbocation due to its Pressum effect, so that lone pair of chlorine is forming a bond here, simultaneous shift of electron pair like this. We get this canonical structure with a negative charge and a pair of electron here, and then this pair of electron can move in this direction. In the sense, it forms a bond pair in between these two positions. To maintain the valency of carbon, this pair of this pi bond will be shifting in this direction, and when this pi bond is shifting in this direction, one electron is given to this carbon so that its positive charge is neutralized. So we get the stabilized carbocation, where now the positive charge is over Cl. Now then this ion can come back to the benzenoid structure. This is unstable, this is an intermediate. Now this intermediate will remove H as H positive, and then this Cl bond between Cl and C is shifting over Cl. In the sense, this bond pair will be taken up completely by the orbital of chlorine, so that the chlorine is now getting the share of electron here, and its charge is getting neutralized, and H is removed as H positive, and we get the product Cl E, the electrophile, then bond here, and bond here for the product. So the speciality is that the intermediate, and through the intermediate, the transition state also is stabilized by involvement of chlorine. That is, plus some effect of chlorine can stabilize both the transition state and the intermediate. Then coming to nucleophilic substitution reactions of chlorine. Now, I told you earlier that the impossible can be made possible by extreme conditions like high temperature, high pressure, and even the presence of a catalyst. So, chlorobenzene can be converted to the corresponding hydroxy derivative called phenol. You replace Cl by OH, and for that process we require NaOH. Then about 600 to 630 Kelvin temperature, then about 300 atmospheres of pressure. Then Cl combines with H of NaOH and we get ONA, and then on reaction that NaCl is removed and H gets the position of Na, and OH phenol is formed. See, phenol is acidic, that is why we get the sodium salt of phenol as the product, because the medium contains the base. So whenever phenol is formed, that will react with the sodium hydroxide, which is a base, and the phenol is acid. So acid base reaction forming salt, and this salt has to be converted to the free acid, that is phenol, by reaction with a strong mineral acid like HCl. So we are using extreme conditions, and this temperature, a range of temperature is used. You need not remember the exact temperature, but you write it as 600 or 630, there is no harm. And the pressure is 300, it is easy to remember, and this is the method of manufacture, that is preparation of phenol on a large scale. That is, manufacture of phenol is done by this process. Sodium hydroxide, 300 atmospheres of pressure, temperature between 600 and 630 Kelvin. Now, the nucleophile is prevented from attacking chlorobenzene. One reason is that the electron density, pi electron density of the benzene ring repels the incoming electron pair of the nucleophile. So if the pi electron density is withdrawn from the benzene ring by attached groups which are strongly electron withdrawing, one such group is a nitro group. A nitro group, due to the presence of greater number of electronegative atoms, that is nitrogen and oxygen, and again showing minus M effect, it can show both minus M and minus I effect. So electron density may be withdrawn from the benzene ring, so that a nucleophile can attack. Now consider para-nitrochlorobenzene. Now here, due to resonance, the minus M effect of nitro group, this pair of electron moving in this direction, and simultaneous movement like this and simultaneous movement like this creates a positive charge at the alpha carbon. So this alpha carbon possessing positive charge, see, this is a canonical structure, so in the resonance hybrid the alpha position will possess partial positive charge, and OH minus can attack this alpha carbon because of its positive charge, partial positive charge character. In presence of NaOH, OH minus will be attacking this alpha carbon. We get an intermediate like this, Now this intermediate can return back to the phenolic structure. First of all, the electron pair over O negative of nitro group shifts in this direction. Then valency of nitrogen will be raised. This pi electron will be shifting in this direction. Then valency of this carbon will be raised. Then this pi electron will be shifting in this direction. Valency of this carbon will be raised. Then Cl is removed as Cl negative. So we get OH. But in alkaline medium, phenol is acidic. So that we get the salt of the acid H positive is removed by Na positive, H and OH combining, and removal of water ONA. Then we have to use a mineral acid, say HCl, so that NaCl is removed and OH free phenol is formed. Now suppose we are having two nitro groups, then the partial positive charge at the alpha carbon is increased in magnitude. Then the conditions required is a still milder condition is only required for removal of Cl by OH. Now in the previous case, we used in the case of para-nitrochlorobenzene, we used about 440 Kelvin and NaOH. So high temperature 440 Kelvin was used as temperature. Now here the temperature used is 370 Kelvin. A lower temperature can affect this reaction because the two nitro groups, this nitro group will create a positive charge here by shifting this electron and shifting this electron. So you get a positive charge at the alpha carbon. Now again the magnitude of this positive charge is increased by the mesomeric effect of nitro group, so that electron pair is driven in this direction. So again positive charge is created. This means the combined action of nitro group increases the magnitude of partial positive charge at the alpha carbon. So a speedier reaction can occur with OH negative, and we get (2,4) dinitrophenol. So the extent of positive charge at the alpha carbon is increased by increasing the number of nitro groups in the ortho and para position. Now finally, when we come to a trinitro derivative, that is the ortho and para positions are substituted by nitro groups, then the magnitude of positive charge created at the alpha carbon will be very high, so that the conditions required is very mild. When we warm this with water, so high temperature is not needed, NaOH is not needed, even water can hydrolyze this compound to phenolic compound. So H of water combines with Cl producing HCl, and OH of water takes the place of Cl, and we get 2, 4, 6 trinitrophenol, and this is called picril chloride, and this compound is called picric acid. So this compound is phenol is acidic, and the three nitro groups with a strong minus I and minus M effects will make this compound highly acidic. So the acidity of phenol is very highly increased by 3-nitro group, hence it is called picric acid. The acid term acid indicates that it is very highly acidic. So picril chloride can be hydrolyzed by warm water, and Cl is replaced by OH. Coming to the reaction of chlorobenzene with metals. As in the case of Wurtz reaction, chlorobenzene can react with another chlorobenzene molecule or an alkyl halide molecule. How a haloalkane can react with chlorobenzene or a haloarene can react with chlorobenzene. Now these two reactions are known under two different names. If the haloalkane and chlorobenzene react, then the reaction is called Wurtz-Fittig reaction. Wurtz-Fittig reaction. And if two haloarenes are reacting, then the reaction is called a Fittig reaction. So in Wurtz-Fittig reaction, the haloarene reacts with a haloalkane with the sodium metal in triether removal of 2NaCl, and we get a hydrocarbon. This is toluene. And if two haloarenes are reacting, then the reaction is called a Fittig reaction. A removal of 2NaCl, we get biphenyl. This is also called diphenyl. So Wurtz-Fittig reaction and Fittig reaction. Then with the magnesium in either, chlorobenzene can react in triether to form phenyl magnesium chloride, that is a Grignard reagent. Then coming to some questions in the text. Now you are given two haloalkanes, that is 1 bromobutane and 2 bromobutane. Now it is asked that which of the following pair reacts more rapidly by SN2 mechanism. Now here we can say there is an alpha branch and there is no branching at the alpha carbon here. So in this compound, so compound 1 and compound 2, if there is alpha branching, then there is great steric crowding in the transition state for SN2 reaction because there are two alkyl groups. Here there is only one alkyl group and hence it is a long chain. This methyl group and this CS2 or CS2 will not interfere with sterically interfere with the coming nucleophile, so that this molecule cannot easily undergo SN2 reaction because of the steric repulsion of these two groups with the incoming nucleophile in the SN2 reaction. So one reacts faster, we can say. Now the reason is binding at alpha carbon decreases SN2 rate but increases SN1 rate. Alpha binding increases steric clouding in the transition state of SN2. Now two other compounds are given, that is 1, 2, 3, 4. So 2-bromobutane and this is tertiary-butyl bromide. Of course, there are three alkyl groups in tertiary-butyl bromide, whereas there are only two alkyl groups. So alpha branching is higher in this compound, and when alpha branching is higher, the SN2 rate is lower. So this compound 1 reacts faster. By SN2 because in 2 there is alpha branching, higher alpha branching, and this causes greater steric clouding, steric repulsion in the SN2 transition stage. Now then two more compounds are given. CH3, CH, CH3, CH2, CH2, Br. Then another compound is CH3, CH2, CH, CH3, CH2, Br. Now the main difference between these two compounds is that in compound 2 the branch is close to the alpha carbon. In compound 3 the branch is, this is the branch, and here this is the branch. In compound 2 the branch is close to the alpha carbon, and in compound 3 the branch is away from the alpha carbon. So great steric crowding will be observed in the case of compound 2, because in compound 2 the branch is close to the alpha carbon, so that compound 1 can react easily by SN2 mechanism. 1 reacts because branch is away from alpha carbon. So that is the reason now two compounds are given. And it is asked which undergoes SN1 faster. Now evidently the compound 1 undergoes SN1 faster because there are 3 alkyl groups, that is CH3, CH3 and CH3, and the carbocation obtained from 1, that is so 1 gives this carbocation and 2 this is a tertiary carbocation and this is a secondary carbocation. So a tertiary carbocation is more stabilized by hyperconjugation and inductive effects. Here the inductive effect of like two groups, that is two ethyl groups, here as here we have 3 methyl groups showing inductive effect, and here we can say 3 plus 3 plus 3, that is 9 hyperconjugation canonical structures. Here only 2 plus 2, 4 hyperconjugation canonical structures. So plus psi of 2 alkyl groups. Here plus psi of 3 alkyl groups, so that one reacts faster. So one reacts faster by SN1. Another set of examples are given, that is one and two. Evidently one should react faster. Because it gives a secondary carbocation, whereas 2 gives only a primary carbocation. So you can say CS3, CS2, 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 CH, Cl, CS3. On ionization gives CH, CS3 positive is secondary, and 2 plus 3 high, 5 hyperconjugation canonical structures, and plus psi of 2 alkyl groups. Whereas in the case of second isomer, it gives only a primary carbocation. CS2, Cl, CS2 positive, primary carbocation. Then here is a CS2 group. So plus psi of 1 alkyl group, then these two hydrogens can get involved in hyperconjugation. So 2 hyperconjugation canonical structures. Then a set of reactions are given, that is bromocyclohexyl. Identify A, B, C, D, E, R and R dash. Now starting from this compound, Br plus Mg. So evidently a Grignard reagent should be formed. MgBr. And this happens in dry ether. Now this one hydrolysis H2. A hydrolysis reaction means